Now I will discuss following articles on friction. Number 1, direction of friction force. Number 2, angle of friction. Number 3, angle of repose. Number 4, role of friction in walking. Between two objects, the direction of friction force is such as to oppose the motion or tendency of motion of one over the other. Let us take few typical examples to illustrate this point. Let us consider a stone dropped on a conveyor belt. Let the conveyor belt is moving rightward with a constant speed v, and a stone is dropped gently on the belt. As initially the stone is at rest from ground frame, but the belt is moving rightward, so relative to the belt the stone is moving leftward, and hence the force of friction that will come into play on the stone is rightward. This is kinetic friction, as there is actual slipping between the two, and it is due to this force of friction the stone gradually gains speed, and ultimately when its speed becomes equal to that of the conveyor belt, it comes to rest relative to the belt. Here, interestingly, the friction is generating velocity of the stone. A second example is of a suitcase kept on the floor of an accelerating train. If the train is accelerating rightward, then from the frame of the train the suitcase experiences a pseudo force leftward, and that gives it the tendency to slip leftward, and so the force of friction on the suitcase here again is rightward. If the suitcase doesn't slip, then the force of friction that is called into play is static force of friction, and it is rightward. Let us take a third example, an interesting example of a sphere rolling down an incline. When the sphere is rolling down the incline, then its point of contact with respect to the inclined plane is always at rest. But the component of the weight of the sphere down the incline, we call it mg sin theta. This component gives it a tendency to slip downward, and so the force of friction tries to prevent this tendency to slip down and acts in upward direction. This force is also static in nature, as it has a tendency to slip on the incline but does not actually slip on the incline. In this case, whether the sphere is rolling down or up the incline, the force of static friction is always up the incline, as the component of weight mg sin theta acts always downward. Next, angle of friction. When the force of friction on an object is limiting, that is, the maximum force of static friction comes into play, then the contact force as we have earlier discussed, Fs max, the resultant of the normal reaction and Fs max is the contact force, and this contact force makes an angle alpha with the normal reaction. This alpha is the angle of friction. As Fs max is equal to mu times the normal force of reaction, so tan alpha, which is equal to mu n by the normal reaction n, is equal to mu, or alpha is tan inverse mu. So angle of friction is tan inverse of the coefficient of friction. Next, angle of repose. When an object is on the verge of sliding down an incline under the action of its own weight, then the angle the incline makes with the horizontal is called angle of repose. If we look at the force analysis, the mg sin theta, the component of the weight down the incline, is balanced by the limiting force of static friction mu times n, where n is the normal reaction force and mg cos theta is the component of weight normal to the incline. Obviously here n is equal to mg cos theta and mu n is equal to mg sin theta. Dividing one by the other, we get tan theta is equal to mu, or the angle of repose theta is tan inverse of mu. Now, the role of friction during walking. When we walk in any step, During first half, we bring ourselves to motion from rest. That is, we are accelerating in forward direction. So, pseudo force Ma acting backward gives us a tendency to slip backward, and so static force of friction opposes that tendency to slip backward and hence act in forward direction. It is exactly other way round during second half of a step. We come to rest from motion, accelerating backward, pseudo force forward, tendency to slip forward, and hence friction backward. Thus, average force of friction during a step is 0. Now, relation between length of step and coefficient of friction. As a man put a step forward, his leg makes an angle theta with vertical. More the magnitude of theta, more will be length of his step. Forces on the man are pseudo force Ma backward, weight Mg downward, and contact force R on the foot. In his frame, the man is in equilibrium, both translational and rotational. Hence, all these three forces must be concurrent. As Ma and Mg passes through center of mass of the man, so contact force R must be along leg. The normal component of contact force R is N. Horizontal component of R is friction force Fs. As Fs by N is equal to tan theta, or Fs is equal to N tan theta, so Fs being less than equal to mu n, we get tan theta is less than equal to mu. That is, the angle theta should be less than equal to tan inverse mu. This explains why smaller the mu, the smaller will be the length of a step. And on surfaces where friction is almost absent, like say on ice or on a piece of floor where oil is spilled, mu is almost 0 and length of step will also be 0. That is, we are not able to walk on such surfaces where coefficient of friction is negligibly small.